Alright, in this video here we're going to talk about solving trig equations. Now, I did another video just now where I talked about kind of the process that we use to solve trig equations, and I did a couple of really simple examples of solving a trig equation. So if you haven't seen that video yet, you might want to check that one out before you watch this one. This one will look at some equations that are a little bit more complicated than the examples that I did in that first video. So the first example here, 2 times sine of theta minus 1 equals 0. Right, so the first thing I need to do if I'm solving a trig equation is isolate the trigonometric term. Right, so this sine theta, I need to get that by itself, which means I need to add this 1 over here and then also divide by the 2. All right, so let's start by doing that. Just like we're solving any other type of equation where we have to isolate something, I do that by just adding, subtracting, dividing stuff to get it to the other side. Right, so I add the 1 and then I divide by 2, so I get sine of theta equals 1/2. All right, sine theta equals 1/2, and now that I have that trig function isolated on one side of the equation and all the numbers are on the other side, now to cancel out that sine function, I can do the inverse sine function on both sides of the equation. All right, so if you've paid attention to the stuff, if you've been watching the other videos that I've done on other topics, just like when you're solving exponential or logarithmic equations, the first thing you have to do is isolate the exponential term or the logarithmic term before you can use the inverse function to cancel it out. Same basic strategy here. If I have a trig equation, I need to isolate that trigonometric term before I can use the inverse trig function, in this case the sine inverse, to cancel it out. Right, which is exactly what we just did. I put the sine inverse on both sides, that cancels out the sine function. So I have theta equals sine inverse of 1/2. And if you watch that other video that I did about solving the trig equations, this is actually the first example that we did, was sine theta equals 1/2. Right, so if you saw that video, you've already kind of seen this problem. So I'm going to go through this part of it kind of quickly because I literally just did this problem like 10 minutes ago when I made that other video. So theta equals sine inverse of 1/2. All right, so I go to my trig hand, right? Sine is the y coordinate, so if I put down my ring finger, my x is above, or root 3 over 2, my y below is 1/2. So theta is going to, or sine inverse of 1/2 is going to be this finger, which corresponds to pi over 6. All right, so theta equals pi over 6. Remember, when we're solving trig equations, we give our answers in radians. And if the numbers that we have here, in this case the 1/2, is something we know from the unit circle, we use the unit circle to give the exact value. If it's a number we don't know, if this was like sine inverse of 0.5397, and that's not a number that we have on the unit circle, then we use the calculator and we get the approximate solution, some decimal number that we round off. But if we can give the exact value from the unit circle, we want to give the exact value. All right, so theta equals pi over 6. Now, is that the only solution? Well, no. All right, trig equations don't ever have just one single solution. All right, so pi over 6, remember that's up here. All right, here's my angle, pi over 6. And the terminal point for that, as we just saw from the trig hand, was root 3 over 2, comma 1/2. It has an x coordinate, it has a y coordinate of 1/2, which is why sine of pi over 6 equals 1/2, right? Remember, the definition of the sine function, it gives you the y coordinate of your terminal point. All right, now the question is, well, where in the first period of this sine function between 0 and 2 pi, where else is y going to equal 1/2? Well, y is going to equal 1/2 over here in the second quadrant, right, where it's going to have the terminal point negative root 3 over 2, positive 1/2, right, and y once again equals positive 1/2. All right, so when you're solving a sine equation, you get your answer from the first quadrant, and then you're going to reflect that over into the second quadrant to get your other solution. If you're solving a cosine equation, like we saw in that last video, the last example I did was a cosine equation. If you get your answer in the first quadrant, for cosine, you have to reflect it down into the fourth quadrant to get the other solution. All right, so, but if you don't have to memorize that. If you just think about it, all right, so sine is the y coordinate. This is where y is positive 1/2. Where else will y be a positive 1/2? Well, it's not going to be down here, right? Because in the fourth quadrant, y values are negative. It's got to be over here in the second quadrant where y equals a positive 1/2, right? And then the other thing is, what's this angle over here, right? Well, that angle is going to be 5 pi over 6, right? That's the angle that's pi over 6 less than pi, right? So if you're not sure about that, remember, the negative x-axis, that's an angle of pi radians, and use symmetry. If this one is 0 plus pi over 6 on this side, this one on this side is pi minus pi over 6, right? And if you find a common denominator and subtract that, you're going to get 5 pi over 6. right? So theta also equals 5 pi over 6. Right, so those are our two solutions in one period of the graph of this function, right? Just between 0 and 2 pi, those are the 2 points on the unit circle where sine, or where the y-coordinate, equals 1/2, right? And those are the only 2 points on that one lap around the circle, all right? So these are my solutions in one period, but if I want to give all of the solutions of this trig equation, remember what we have to do, and I explained this in that last video that I did that I mentioned before, I have to add to that 2 pi k to each of those solutions. Remember that the k represents any integer, so any positive or negative whole number, and the 2 pi is your period for the sine function. Right? So this is saying if I go to pi over 6 on the unit circle, and then I add 2 pi to it any multiple of times, right? K can be, 5 times 2 pi would be like doing another 5 laps around the circle. -3 times 2 pi would be like going 3 laps around the circle in the negative direction. But no matter how many multiples of 2 pi I add or subtract to pi over 6, I always end up on that same spot, and the sine of that point, or that angle, is always going to give me 1/2, right? And same idea for 5 pi over 6. If I go to 5 pi over 6, and then I go, any multiple of 2 pi in any direction around the circle, I end up at the exact same point, and the sine of that angle is still going to be 1/2. All right, so those are all of our solutions to this original equation, right? So solving a trig equation, first thing, isolate the exponent, or not the exponential, isolate the trigonometric term if it's not already isolated, right? So you have to like add, subtract, move numbers to the other side, divide by the 2 in this case, and then if this number is from the unit circle, you can use your trig hand, you can use your knowledge of the unit circle to figure out the solution. Then use the symmetry to figure out where the other solution is going to be. Almost always when you're solving these trig functions, you're going to have 2 solutions on the unit circle. Not every single time, but almost always you will. So you always have to look for that other solution. And then don't forget to give all of the solutions to the equation, you have to do that plus 2 pi k to each one of your solutions from that first period of the graph between 0 and 2 pi. All right, so that's our first example, solving 2 sine theta minus 1. And once you get to this point here, sine theta equals 1/2. If I went too quick for that, if I didn't explain it well enough, go back and watch the first video that I did on solving trig equations. That was the first example I did. It just kind of started from this point right here. That was the equation we were given. And I explained in a little more detail how to solve that. So you might want to go back and check that one out to see if what I did here didn't make sense to you. All right, but I'm going to pause the recording now and erase this example and then put up the next one that we'll do on this video. All right, the next example we're going to do, we have tangent squared of theta minus 3 equals 0. Right, so here we have an equation that involves the tangent function. So this one's going to be a little bit more complicated than the sine or cosine equations, but nothing too bad. All right, so first thing I want to do is isolate my trigonometric term, which means first adding this 3 over to the other side. All right, so I get tangent squared of theta equals positive 3. And then since I have a tangent squared here, well, to cancel out that second power, I do the square root, right? The square root is the inverse of the second power. So that's going to give me tangent of theta on the left side equals plus or minus square root of 3 on the right side. Now remember, just like when you're solving a quadratic equation, x squared equals 16, and you have to do a square root on both sides, you have to put the plus or minus on that square root that you put on the other side of the equation from the x. That's the rule for doing square roots in an equation, no matter what's being squared, whether it's an x squared or a tangent squared. When I do the square root on both sides, I have to put that plus or minus there. Right, so I'm looking for where does tangent theta equal positive root 3, and also where does tangent theta equal negative root 3. All right, so think of it in terms of the inverse function, right? To cancel out the tangent function, I have to do the inverse tangent. All right, so theta is going to equal tangent inverse of positive and negative square root of 3. So there's really 2 different things here. There's tangent inverse of positive square root of 3 and tangent inverse of negative square root of 3. All right, let me maybe make that 3 big enough that y'all can see it. All right, so that's what we got. So now we got to figure out, if I go to my unit circle, now remember, for the tangent inverse function, the period for the tangent function is pi, right? The tangent function goes from negative pi over 2 to positive pi over 2, right? And then it repeats the graph over and over again, right? If you recall real quick, and if you haven't seen the videos that I did about the graphs of these functions, you might want to check them out. But the tangent function goes like this, where the period is pi. Right? It goes between negative pi over 2 and positive pi over 2. That's where it has vertical asymptotes, so the length of the period is pi before it starts to repeat itself. So different from the sine and cosine functions that we did earlier in this video and in the other video that I did, where at the end we had to add the 2k or 2 pi k to our answers because the period of sine and cosine was 2 pi. For the tangent function, we only have to look for answers between negative pi over 2 and positive pi over 2, and then just add 1 pi k to that because the period of the tangent function is just 1 pi as opposed to 2 pi. All right, so basically, when I'm solving the tangent function, I don't have to worry about that left side of the unit circle. I'm just looking on the right side, and where does tangent over here equal positive root 3, and where does it equal negative root 3? What we call tangent is the y coordinate over the x coordinate. All right, so if I do the y over the x, I have to get root 3. So let's see. If I do this finger here, which is the one that corresponds to pi over 3, right? So pi over 3, I would have a y of root 3 over 2 and an x of 1/2. So the terminal point for pi over 3 is 1/2 comma root 3 over 2. And if you don't know what I'm doing with my trig hand, go back and watch the video that I did on the unit circle and trig hand to be able to find those numbers, just putting down some of your fingers. So it's 1/2 root 3 over 2. If I do the y over the x, right, root 3 over 2 over 1/2, the 2's cancel out, and that's going to equal positive square root of 3. Right, so pi over 3 is going to be one of my solutions here. So theta equals pi over 3. Right, because there, if I do the y over the x, which is the definition of tangent, I get positive square root of 3. All right, which tells me that the other one, to get negative root 3, is probably going to be down here at negative pi over 3. Right, that terminal point is going to be x equals positive 1/2, y equals negative root 3 over 2. Right, and once again, I'm using the symmetry of the unit circle. When I reflect this point down into the second quadrant, the x coordinate is going to stay the same because I still have positive x values. I'm over on the right side, but the y coordinate up here becomes negative because I'm flipping that down into the negative y values. Right, and if this angle up here is positive pi over 3, the one down here is just negative pi over 3, right? It's the same angle, just going in the opposite direction. So I just put a negative on that angle, right? And here, once again, if I do the y over the x, just like I did a minute ago, now it's negative root 3 over 2 over 1/2. Once again, the 1/2's cancel out, and I get negative square root of 3, right? So tangent inverse of negative square root of 3 is going to be negative pi over 3, right? So those are my two solutions in one period of the tangent function, right, between negative pi over 2 and positive pi over 2. Remember, for tangent, the period is only pi, right? Sine and cosine, the period is 2 pi, right? It takes the graph 2 pi units before it finally gets back to the starting point and repeats itself. But for tangent, that happens between negative pi over 2 and positive pi over 2. So the length of the period for tangent is only 1 pi, right? So I find all of my solutions in half of the unit circle between negative pi over 2 and positive pi over 2, right? So that gives me the pi over 3, negative pi over 3 are my solutions in that one period. And then to give all the solutions, I add plus pi k, right? Not plus 2 pi k with sine and cosine, right? Because for sine and cosine, the period is 2 pi, so I have to add 2 pi k to it. For the tangent function, the period is 1 pi, so I add 1 pi k to each of my answers, right? You don't have to put the 1 in front of the pi. You can just add pi k, right? So that's the key difference between solving a tangent equation and solving sine and cosine. For sine and cosine, you do just like we did that example earlier, and the ones I did on the other video. You do them just like that, right? For tangent, you just look at the solutions on the right half of the unit circle. That's one full period of the tangent graph. And then you add just a 1 pi k to it because the period of tangent is 1 pi. All right, so that's solving some slightly more complicated trig equations than the ones that I did in the first video. But I'm going to do another video now where the equations get more complicated. I'm going to do several more videos where in each one the equations get a little bit more complicated than the ones that came before. So keep on watching the ones that I'm doing. Because trig equations do get pretty complicated, right? So make sure you understand how to do those more difficult ones.